All right, so let me go ahead and finish up the last remaining concepts regarding mass spectrometry. We go ahead and go back to this. Okay, so here is the situation. So we already went over the fundamentals of mass spectrometry, what gives rise to mass spectrum, principles behind it, etc. What are the main fragmentation patterns? So here I'm going to discuss, can we actually, from a mass spectrum, deduce what is the molecular formula of a molecule? Because knowing the molecular formula goes a long way towards us being able to come up with a structure. So many textbooks, including the Klein, discuss what is called doing this via an analysis of the M+1 peak. Remember, the M+1 peak is a result of C13 being in the molecule. So here's how you would do this. So you recall that isotopes are going to differ from each other only on the number of neutrons that they have the same number of protons and electrons. So if we're looking at carbon, there are three main naturally occurring isotopes of carbon: carbon-12, carbon-13, and carbon-14. Of these, carbon-12 is the most abundant. It makes up 98.9%, and carbon-13 is the second most abundant at about 1.1%. Carbon-12 is really far, far less abundant, and I'm showing you there in the last bullet point what percentage it constitutes. And so for purposes of the calculation here, it doesn't really play a part. So remember, the key here is the two most abundant naturally occurring isotopes of carbon are carbon-12, carbon-13. Carbon-12 makes up 98.9% of all carbon atoms on Earth, and carbon-13 makes up 1.1% of all carbon atoms on Earth. So, since in a mass spectrometer, each individual molecule, right, is going to be ionized, for example, by crashing an electron into it and causing the ejection of an electron from the molecule, then we're going to detect the ions, positively charged ions. So let's look at methane. Methane, I'll remind you, is CH4. So we're looking at this molecule, organic molecule. It has one carbon. So that means that 98.9% of the molecular ions that are going to be detected will contain a carbon-12 atom, and 1.1% will contain a carbon-13 atom. Remember, the molecules that have a regular carbon-12 is what gives rise to your molecular ion or parent ion or M+ peak, while the molecules or the molecules that have the C13 be those that will give rise to a peak that comes out M+1, 1 unit more than the molecular ion. This means, based on percentages, the relative height of the M+1 peak is going to be 1.1% compared to the height of your molecular ion peak, right? As I say here, the relative height of the M+1 peak is 1.1% as tall as your molecular ion peak. Now, if the molecule has more carbon atoms than one, right? So instead of methane, which has one carbon, what if we're looking at decane? It has 10 carbons. In that case, the relative height of the M+1 peak will be 1.1% multiplied by 10, which would be 11%. If I'm looking at icosane, which has 20 carbons, then 1.1 times 20 is going to be 22%. for looking at pentane, which has 5 carbons, then the M plus 1 peak will be 5 times 1.1, which is 5.5%. 5.5% or 11% or 22% relative to the height of your molecular ion peak. This is the basis for this calculation that's done analyzing the M plus 1 peak. Now, just as a disclaimer, to be perfectly accurate, there are some other isotopes that can contribute to the M plus 1 peak, but they're so much less abundant than C13 that mathematically it doesn't really have an impact, and we can do the calculation I'm about to show you. So if we have a mass spectrum, and a mass spectrum here is what it is on the left, but our instruments, modern instruments, will also give out a readout such as this. In other words, for every peak that you see, a peak here, a peak there, a peak there, here, 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 all of these peaks, it gives me what is their mass or mass to charge, right? So 1 at 15, 1 at 26, 27, 28, 29, 38, 39, 41, so on and so forth. And it gives me the relative height here of each one. So at 15, it's 4.8%. At 26 is 1.3%. At 27 is 10.5%, and so on and so forth. Now remember, we can find what the molecular ion peak is. It is the one that has the highest mass. Now that we know that we typically get the M plus 1 peak, we have to take that into account. So therefore, this peak here that I've circled is a molecular ion peak. So this little one down here is therefore the M plus 1 peak, right? So this is the M plus 1 peak. This is the molecular ion peak. That is the information that we need in order to come up with a molecular formula for a given molecule. So we are going to focus on molecular ion peak, which is 86, and the M plus 1 peak, which is 87. From that information, here's how we're going to do it. So walking through this, and this example I just took straight from the client textbook. We need to know how the M plus 1 peak height compares to the height of the molecular ion peak. So to do this, we look at the relative height of the M plus 1 peak, which is 1.2%, and the height of the molecular ion peak, which is 20.9%. And we do, what we find is what is 1.2 as a percentage of 20.9. So here is the calculation. 1.2% over 20.9 multiplied by 100% will give us what is 1.2 as a percentage of 20.9. Again, 1.2 being the height of your M plus 1 peak here, and 20.9 being the height of my molecular ion. That comes up to 5.7%. Now, since each carbon in the compound contributes 1.1% to the height of the M plus 1 peak, based on the relative abundances, we divide this result, the 5.7, by 1.1, we get this ratio of 5.2. That should represent, right here, the number of carbons that this molecule contains. Now, since we can't have a fraction of an atom, we can't really have 5.2 carbon atoms. What you do is you just round it to the nearest whole number. So this tells us that this molecule should contain 5 carbon atoms. All right, so there we've determined the number of carbon atoms that we have in this molecule. So then we know the molecular ion has a mass of 86. I'll go back and show you right here. So that is the mass of the molecular ion. That is the weight, the weight of your molecule. It's 86. If we know that we have 5 carbons, then 5 carbons account for what mass out of the total 86? Each carbon has a mass of 12. 5 times 12 is 60. So 5 carbons account for 60. So therefore, if we subtract 60, the mass from the 5 carbons, from the total mass of the molecule, we get 26. So the question becomes, could the formula simply be C5H26? And the answer is no, because if a molecule has 5 carbons, it cannot have 26 hydrogens. How do we know that? I'll remind you. The class of molecules that is said to be fully saturated, remember from your Orgo 1, which means that it contains its full complement of hydrogens, be your alkenes. And alkanes have the formula CnH2n plus 2. So the number of hydrogens can only be 2n plus 2, where n is the number of carbons that I have. So therefore, if I have 5 carbons, 2 times 5 plus 2 equals the maximum number of hydrogens that that molecule can have, which is 12. 26 is way more than 12. So we know the formula is not only C5H26. There must be some other element. Here, we have to make informed, educated assumptions. What element could that be? First of all, we know it cannot be nitrogen. Why not nitrogen? Because of the odd number rule. That if I have a nitrogen, an odd number of nitrogens to be technically accurate, the molecular ion is going to be an odd number. But here the molecular ion is 86, which is even, so it's unlikely that there is a nitrogen. What about an oxygen? Now, if you ask yourself, why do we narrow in on nitrogen and oxygen? Because by far, those are the two most likely elements that I'm going to have in an organic molecule. That's why we go there first. So we've discarded the possibility of nitrogen. So then we say, could it be oxygen? Okay, let's assume there is an oxygen. An oxygen has a mass of 16. We already determined that the 5 carbons account for 60. So one oxygen would account for 16, a total of 76. So could the formula be 5 carbons, which would be 76, and 86 minus 76 is 10. Could this be the number of hydrogens? So in other words, could the formula be C5H10? Oh, well, we already determined that if I have 5 carbons, then the maximum number of hydrogens here can be 12. 10 is within that range. So then, yes, this is a perfectly reasonable formula. That's what it is. Now, remember, we now have the ability to recognize if there's a chlorine, a bromine, a sulfur, an iodine, along with nitrogen. And since oxygen is the most commonly other element found with carbon and hydrogen, see, we can essentially tell what other element you might actually have there. So here's another example that I took from the client textbook. So what you should do here is pause the video and see if you can work it out by yourself. So pause it here, and then I'll show you how it's actually worked, and you can compare. Pause here. All right, coming back from this pause. Here, the molecular ion is 73, the M plus 1 is 72, and the M plus 1 is 73. So they tell us the relative height of the molecular ion is 38.3. The relative height of the M plus 1 peak is 1.7. First thing we want to do is find what is 1.7 as a percentage of 38.3. So therefore, I multiply by 100% to get that percentage using my handy dandy cell phone. 1.7 divided by 38.3 multiplied by 100 to get percentage is 4.4. Let me do that again. 1.7 divided by 38.3 multiplied by 100. Yeah, 4.4 percent. We now want to divide this 4.4% by 1.1 because that's what each carbon contributes. And you can see that that's going to be 4. This is equal to the number of carbons that we have. Now, 4 carbons will be 4 times 12, since each carbon is 12, which means a mass of 48. We know that the mass of the molecule is 72. So therefore, 72 minus 48 is going to be 24. So the question is it possible for the formula to be 4 carbons and the remainder would be your hydrogens, which would be 24? No, that is not possible, because if I have 4 carbons, 4 times 2 is 8 plus 2 is 10. Maximum number of hydrogens that I could have be 10. So let's go look at our 2 most likely culprits for the remainder of the mass: nitrogen, oxygen. Is it nitrogen? No, because my molecular ion is an even number. So therefore, what if it's oxygen? Okay, well, if it's 1 oxygen, then oxygen has a mass of 16. Since we already know, so we know the total mass is 72, we know there are 4 carbons, which is 48. If there is an oxygen, that would have a mass of 16. So then the question is, what is 72 minus 48 minus 16? That would be 8. So is it possible that this equals the number of hydrogens? Well, the number is within what I could have if I have 4 carbons. So is the formula C4H8O? And the answer is yes, that must be the molecular formula of my molecule. Now, sometimes we don't have the M+1 information, but we do know what the molecular ion is. But somehow the M+1 peak isn't there. We don't have it. The information is not provided. What we can then do is invoke what is called the rule of 13. Now, the rule of 13, to be perfectly clear, applies for hydrocarbons, for molecules that contain only carbon and hydrogen. But of course, we can deduce the presence of something else, as we just did when we were doing analysis of the M+1 peak. The way we're going to do this is we take our molecular ion and divide by 13. However many times that 13 goes into the molecular ion, that equals the number of carbons. That number plus whatever remainder I have must equal the number of hydrogens. Now, if that total is the same as the molecular ion, then all you have is a hydrocarbon, and that's it. If it's less than, then, of course, it means you have some other element, and it might be nitrogen or oxygen most commonly. And you, of course, can deduce if it's an iodine, a sulfur, bromine, chlorine, right? Same thing. So here's an example. Suppose you find out, or you look at the mass spec, and you can tell that the molecular ion has a mass of 106. So I take 106 and I divide by 13. That gives me 8 remainder 2. So that means 8 is equal to the number of carbons that I have in the molecule. And 8 plus 2 here, which is 10, should equal the number of hydrogens that I have. So the formula should be C8H10, right? Very simple. What if you have a heteroatom? In other words, if you have something else? Well, we simply have to account for it. Let's say that you have a molecular ion, or you're given a mass spectrum, and it has a molecular ion of 102. And let's say that you know, or you're told that it has an oxygen atom. Before you divide 102 by 13, I have to subtract the mass of the oxygen, right? That's all. So 102 minus 16, because that's what oxygen happens to be. That's going to be 86. So this is what we will apply the rule of 30 into. 86 divided by 13, right? You plug that into your calculator. 13 goes into 86 6 times. And that is 78. 6 times 13 is 78. So therefore, the remainder is 8. So we would say the number of carbons is 6. The number of hydrogens is therefore 6 plus 8, which is 14. So based on all of this, C6, H14O, that would be the molecular formula of my compound. So 6 carbons, 6 times 12 is 72, 14 hydrogens, and 1 oxygen, right? Do the total, and it has to come up to 102. So this is an alternative way, right, when you don't have the M+1 peak information as we had before. All right, a few remaining things to point out that what we just went over in the first video plus just now is the basics of it, but I do want to point out a few other things, especially because Klein does, when you read it, this is what they're saying. There is such a thing as high resolution mass spectrometry. So what do we mean by this? We mean that if you have enough money, you can buy a mass spectrometer that has improved, enhanced resolution. It is better than just your average typical mass spectrometer. What this high resolution mass spectrometer does is it can actually distinguish masses up to 4 decimal places. The reason where this can become very useful is as follows. First of all, a little reminder. So remember that we generally say hydrogen has a mass of 1, carbon 12, oxygen 16, and so on. But masses are generally not whole numbers if you look at the periodic table, right? And that is because you have to, that's giving you the average taking into account the relative abundances. But here is the point here. If the mass of an atom is going to be due to protons and neutrons, protons plus neutrons, I can't have a fraction of a proton or a neutron, so therefore it's always a whole number. But of course, that doesn't factor in the different isotopes and their relative abundances. So really, right, we have to take that into account. But also, let's actually look at the mass of these subatomic particles. A proton is not really one. It is 1.0073 atomic mass units. And a neutron is not really one. It is 1.0086 atomic mass unit. Now, carbon-12, an atom of carbon-12 is exactly 12.000 atomic mass units because the entire concept of atomic mass units, that scale is based on setting the mass of a carbon-12 atom as the standard. So if we set it as a standard, we already arbitrarily designated the atomic mass of a carbon-12 as exactly 12.0000 atomic mass units. Everything else is by comparison. So that's how we're not going to get whole numbers, right? And a high resolution mass spectrometer will be able to tell the mass of a molecule by actually taking into account more detail, more resolution, so that they can measure masses up to 4 decimal places. Here is what I mean. So let's remind ourselves, we say when we, like if I have a molecule, let's say CH4, we say that the mass of this is 16. Why? Because carbon is 12 and each hydrogen is 1, so 4 times 1, we add those up and that is 16. But carbon is really 12.0000. And each hydrogen is not 1, it is 1.0078. So to this, I should add not 4 times 1, but 4 times 1.0078. If I do this, let me do this on my calculator here. So 1.0078 multiplied by 4 is 4.0312. And if I add 12.0000, that will give me a total mass of 16.0312. That is the actual mass. Now, if a mass spectrometer does not have the ability to measure masses up to 4 decimal places, you lose that detail. Here is where that can actually come in handy. And this table is just showing you for other things, like a deuterium is not 2, but 2.0141. A C13 is really 13.0034. Let's say an oxygen is not really 16, it's 15.999.9949, etc. Here is where we see this at play. If I look at these two molecules, each one has 6 carbons and 12, the one on the left has 6 carbons and 12 hydrogen. So we would say 6 times 12 for the carbons is 72, 12 times 1 for the hydrogen would be 12, 72 plus 12 is 84. The molecule on the right here has a formula C5H8O. So 5 carbons would be 5 times 12, which is 60. Each hydrogen would be 1, 8 times 1 is 8, 60 plus 8 is 68, and the oxygen would be 16, so therefore that would give us 84. So how would a mass spectrometer allow us to tell the difference between these two, to distinguish between them? Well, the way we would do this is a high-resolution mass spectrometer would look at the masses, the relative atomic masses, up to 4 decimal places. So for the one on the left, what I have is 4 carbons. So 4 times 12.0000. And there are 12 hydrogens. So 12 times not 1, but 1.0078. If I add that, that comes out to 84.0936. For the one on the right, if I have 5 carbons, that's 5 times 12.0000. I have 8 hydrogens, so that's 8 times 1.0078. And I have 1 oxygen, so that's 1 times 15.9949. I sum that up, and that comes up to 84.0573. So you notice, highly resolved, the masses are not identical. They're not 84. And if the instrument is a high resolution instrument, it can tell masses up to 4 decimal places. It certainly can distinguish 84.0936 from 84.0573. That is the function of high resolution mass spectrometry. Another thing is that mass spectrometers are normally hooked up to some other instrument. For example, one of the most common ones is to connect a mass spectrometer to a gas chromatograph, and that gives us a technique that's called gas chromatography mass spectrometry. So here, we take our gas chromatograph and we have a connecting unit here, and then we connect that with our mass spectrometer. Why this is very useful is gas chromatography. What it does is if I have a mixture of molecules, it separates them out. So it separates them out. So let's say that I have 3 molecules, A, B, and C. When they get to the output here of the gas chromatograph, A, B, and C don't get there at the same time. They get there at different times because the gas chromatograph has already separated them out. And so each of the 3 components of the mixture passes through the mass spectrometer one at a time, and I can therefore get much better results with the mass spectrometer because it's analyzing each molecule one at a time. So the mass spectra that I get is for each molecule one at a time. Right? So this is a very valuable way of doing things. So the GC will give us, gas chromatograph gives us a chromatograph. So here, right, for example, would be a mixture that has 5 things. And I see 1, 2, 3, 4, 5 different peaks for the 5 components, and those reach the mass spectrum one at a time. So the mass spectrum will now analyze each component in that 5-component mixture one at a time, the results, of course, are good. So as an example, I've told you there, blood is a mixture of many things. Urine is a mixture of many things. So for example, right, if you are at these sporting events, right, there's random drug testing. What happens there? Well, they randomly select people from the finals of, let's say, track and field. 100 meters, you go immediately as soon as you're done, they pull you over. If you're randomly selected, you go to a back room and you have to provide a urine sample. And that urine sample is first passed through a gas chromatograph to separate out the components. And then each one is passed through the mass spectrometer, and you can get enhanced results that way. Now, remember I said earlier that there can be cases where your molecular ion peak doesn't appear in your mass spectrum, and that is because 100% of your parent ions fragment, right? Most of the time, not all, most but not all of your parent ions fragment. Some are still remaining, and we can, of course, see them by the detector. If I have a situation where I am interested in knowing what's the molecular ion peak, but it doesn't appear because the molecule fragments because I used a hard ionization method, I can then use a soft ionization method. I mentioned that earlier. An example of that is electrospray ionization. What happens is here, a high voltage needle is going to spray a liquid solution of an analyte into a vacuum, and that causes the ionization. It's a much softer technique, which means that not all of your parent ions are going to fragment to give the fragments that we analyze. This, for example, is used a lot in protein chemistry, because in protein chemistry, we're interested in understanding the structure of the entire protein as well as in the fragments that we actually get from that. Now, as a reminder, if we're trying to find molecular formulas and trying to find structure, one good thing to know would be, well, what's the degree of unsaturation of the molecule? Well, our molecular formula allows us to calculate the degree of unsaturation. And of course, we already know how we can calculate the molecular formula from mass spectrometry. We either do analysis of the n+1 peak or the rule of 30. And here is just a quick reminder that you should know how to calculate the degree of unsaturation. In the Klein textbook, it's called the hydrogen deficiency index. I don't really have to show you because you already, of course, know how to do this, right? So this is it really in terms of the fundamentals behind mass spectrometry. Again, you should be taking notes. Hopefully, this is fairly simple enough to understand, but anything you need clarified, any questions, you should ask in class. But again, if you haven't watched the videos, right, classes become less useful.